SwayamPrabha. Digital India. Educated India.
So welcome to the next lecture on the Rayleigh-Plateau instability. In the previous lecture, we left off at deriving the linearized stability equations. So let's quickly recap what we did. We took a stationary filament, considered varicose mode of perturbations, introduced the normal mode form for the perturbation, but we haven't used it yet. But we said that the amplitude of this perturbation is very small, and we got rid of all the axisymmetric terms, and then we linearized the equations. And what we now have is a set of simplified linear governing equations. These are linear axisymmetric partial differential equations. Okay. Now we will introduce the normal mode form. Okay. The normal mode form, we introduce it as follows. Let's say we know if R, this is, remember R is spatially and temporally varying, not the base state. The base state is constant R naught plus e power I omega t plus I kz. Then if the undulations, if the radius of the filament is undulating in the following fashion, you should expect that the velocity field will also undulate in a similar fashion. And we'll see this physically as well when we obtain the velocity field inside the deformed filament. So we can say the radial velocity, which is now going to be a function of r, z and t, will be, there is no mean, so there is only perturbation. Okay, this is the amplitude of the radial velocity perturbation times e power omega t plus I kz. Similarly, uz of r, z and t will be we'll call it as w of r I kz. And finally, p of r, z and t will be some p of r e power omega t plus I kz. So let's see how do these modes appear. Now we have to remember that u of r, w of r, p of r are in general complex functions. And this is important and also necessary. Why it's mathematically we'd expect it to be a complex function? Because the other term, which is an exponential term that we have, e power I kz, omega t plus I kz, that's a complex function. So you can actually, the u of r can be complex, but ultimately remember we are going to take the real part of this quantity. But we should also expect it to be a complex function because we have assumed that all the perturbations for ur, uz and p, they're just in this form exponential of omega t plus I kz. There is no phase information, right? We could either put in an explicit phase information, or we could just say that the complex part of ur, w of r and p of r will take care of the phase information. Why do I need to worry about the phase information? We will look at the velocity field inside this perturbation, and this will tell us about the phase relationships between these amplitudes u, w and p. To do this, what I'm going to now do is to take a filament and create an undulation on the filament. I have a crest here, and then I have a depression here, I have a crest here and another depression, right? So the locations where I have the crest and the depression, I'll mark it. For example, somewhere here, the radius is at its maximum. Somewhere here, the radius is its minimum. And again, the radius reaches its and somewhere here again, the radius reaches its maximum. We also have some locations, intermediate locations in the middle, and this will become important in a minute. So when I go from this point to the second maxima, I have basically completed one wavelength, and we have a similar one on the other side. So I have a maximum here, I have a minima here, I have a maxima here, and a minima here. That's the idea of this varicose mode. Now let's basically draw the shape of the velocity field inside this filament. Let's first look at the streamlines. Let's assume that this is a filament which is bulging out, right? This is at a state, the state at which I have drawn. This is, remember, it's changing in time. So this is at a state, this is bulging out. Okay. So this is in a, let's say in a varicose mode in a bulging state. Meaning it is at that stage where the crests are becoming bigger and the troughs are becoming narrower, right? If in such a situation, what you would expect is that you can actually only bulge out if fluid basically were to travel from the crests, from the troughs into the crests. Right? So this is the nature of the streamlines that you should expect in the flow inside the filament. The fact that I've created this undulation means that I have also set up a velocity field of this kind, right? Now let's look at the let's make a plot of the velocity field at the axis. Okay. Let's look at the UZ. Okay. So if I look at the UZ here, the UZ has zero velocity and the maximum is over here. So the maximum is over here, meaning I'm referring to maybe I should refer to you the minimum is here because it's going upwards, okay, and here it's a maximum. So in other words, my velocity field for UZ would look something like this. This is the magnitude of UZ at r equal to 0 Z at this instant of time, right? So clearly, what does it tell you? It tells you that UZ and r of z comma t are out of phase by lambda by 4, meaning by a factor of lambda by 4 wavelength, they are shifted, right? So where the radius is at its maximum, there the axial velocity is at the minimum. Okay, where the radius at its maximum, you should expect radial velocity, right, and not the axial velocity. So this is a phase information that comes out, right? This is also true for UR and UZ. UR and UZ also are out of phase by lambda by 4 because UR and R are in phase. Okay, so this phase information we don't have to explicitly define. It will be taken care of by the functions U of R, W of R, and capital P of R. Let's now substitute these functions into the stability equations. Okay, substituting the normal mode form of the solution into the linearized equations. Let's look at the R equation, R momentum equation. Or okay, let's do the continuity equation. If you look at the continuity equation, what's the first term that we have? We have del u r by del r, but here only capital U of r is a function of r. So this becomes d capital U of r by dr exponential of omega t plus I kz, plus I have u r by r, that will be capital U of r by r z, plus finally we have w of r e power omega t plus I kz and the derivative of with respect to z, that's ik is equal to 0. Okay, so cancelling out, because it can never be omega e power I omega t plus I kz, because it can never be 0. We have a simple equation, d by dr of capital U plus u by r plus ik of w is equal to 0. Okay, we'll call this equation as A. Okay, R momentum equation, if you were to do this, exactly the same analysis, you would get omega times capital U is equal to minus 1 by rho d capital P by dr. We'll call this equation B. And finally we have Z momentum equation, omega W is minus Ik by rho of capital P. This is equation C. Okay, so now what do we have now? Let's summarize all these equations. Simplified equations. What are the simplified equations we have again? D capital U by dr plus U by r plus Ik omega is equal to 0, IkW, sorry. And then we have omega capital U is minus 1 by rho d capital P by dr, and omega times W is minus Ik by rho of capital P. These are three equations that we have, right? What kind of equations are these? These are coupled linear ODEs. if you remember the lecture on the stability analysis, I said from the linearized equations, when we substitute the normal mode form, what we get are ordinary differential equations or coupled ordinary differential equations. That's exactly what we have got. Okay. So what we want to do is we want to eliminate P from these equations. I want to eliminate P from these equations. How do we do this? We have a relationship between W and P. I can substitute W into the continuity equation, that's equation A. And then the equation A will not have W, it will only have U and P. I can take the derivative of equation A with respect to R, and then I'm going to get dP by dR on the last term, and the dP by dR can now be replaced using equation B. So I leave it to you to do the simple algebra, but if I eliminate equation P, eliminating pressure P from these equations, we get an equation of the form d square u by dr square. That's the equation that we get, d square u by dr square plus 1 by r d capital U by dr minus u by r square minus k square of capital U equal to 0. That's the equation that we get. Okay, so now what we can do is multiply by r square, and we get r square times d square u by dr square plus r d capital U by dr minus 1 plus k square of r square times capital U equal to 0. There's an important result. We have now a single equation for the velocity. Once I know the velocity capital U of r, if I can solve this equation, then I basically know capital U. From knowing capital U, I can calculate dP by dr. And once I know the pressure, I can calculate W. So I know all the variables. Okay. Now, we will use a well-known result. So which is this. If you look at this equation is just the modified Bessel's equation. What's the modified Bessel's equation? I'm writing it in blue to differentiate it from the other equation. The modified Bessel's equation would be of this form: d square y by dx square plus x dy by dx minus x square plus n square of y is equal to 0. General solution of this equation is y of x is c1 in of x plus c2 kn of x. Okay, in and kn, they are called modified Bessel's functions of first and second kind respectively. In is called the modified Bessel's equation of the first kind and kn is of the second kind. Right? Now let's look at, let me separate this discussion. This is just additional information. Now if I were to compare the modified Bessel's equation with our equation D that we have derived, then we can see that the equations are identical for when I make the following change. So in equation D, we get n can be thought of as 1. Okay, n can be thought of as 1. We can also make one more thing. We can replace the r with kr. You can make the substitution, or x you can think of as kx. X you can think of it as kr. Okay, it will not make any change to the rest of the equation, the derivative terms. Okay, so the general solution would be of equation D would be u of r, the radial velocity eigenfunction, will be c1 I1 of x, that is x is kr, plus c2 k1 of kr, right? And what is it that we have not used? We have used the mass balance, we have used the momentum equations, but we still haven't used the boundary conditions. So C1 and C2 will be obtained through those boundary conditions. C1 and C2 need to be obtained using the boundary conditions. Now, it's instructive to look at how do these functions look like. For example, if I were to make a plot of kr, or let's say x versus I1 of x, and I will use, for the other color, I'll make a different color. So this is k1 of x. How do these functions look like? K1 would look something like this. It will diverge as one approaches x equal to 0, whereas I1 on the other hand starts off at 0 and goes like this. So this is I1 of x and this is k1 of x. This information is relevant for us because these functions, modified Bessel functions, they ultimately are the solutions of the velocity field u of r, and you cannot have u of r, as r goes to 0, you cannot have u of r to be very large. So even before we do anything, we can anticipate that this k1 of r is a troublesome term. We have to suppress it, right? So this is a good place to stop here. And let me quickly summarize what we have seen so far. We have written down the governing equations, linearized governing equations, the simplified linearized equations. We substituted the normal mode form and we reduced it to a simple Bessel's equation, right? The modified Bessel's equation. I think it's important to highlight this general solution. Let's call this equation as E. Okay. So in the next lecture, what we will do is we will apply the boundary conditions and we will get the constants C1 and C2, and that will give us the dispersion relation. Thank you.